morning. Today I'm going to talk about an application of embedded systems. So we're going to build an entire system. Sound good? So, consider the following embedded system. Your goal is to design an embedded system board with electronics and sensors that interfaces with a quadrotor's flight control board that will prevent the vehicle from colliding with objects. So that individual sentence alone says you're going to create a board that interfaces with another board. Easy enough, right? So you understand if I say a board, and what is the function of this board? Prevent the vehicle from colliding with objects. So if you start reading all the requirements are going to be associated with that one board. Now that one board, if you read here, does not actually do anything with flight. Nothing with flight. It controls nothing with flight. So that's the first thing, is that when you look at a problem and say, I need to solve this, you need to look at what the requirements are going to be for this, and then you should start sketching out, okay, now what sort of things and concepts do I need to worry about? So what I'm going to do is I'm going to let you read this read this a bit. And I'll put this up a little bit later as you sit here and you do the designs in your group exercises. But okay, so this is identifying and setting up the problem. So the next step that I ask for some specific deliverables. The deliverables that I'm going to ask, and we're going to talk about this a little bit, is which MSP 430 chip would you use board and why? And then I have a reference page that I'll provide, and I'll talk about the steps of why you would do one thing or another. Draw the block diagram of your embedded system, including connection labels, which also means power. All right? Write the software interface description for communications between the board. What did I say is being sent between the boards? A single byte from the board to the flight board, right? And then the flight board is going to send back some sort of acknowledgement. Now, what do you think that acknowledgement is going to be? A single wire that says yes or no? Or if you're sending a byte one way via UART, what do you think it's going to come back the other way as? In fact, don't I say in here it's UART, right? And then finally write the algorithms. So let's take a look at some of the aspects here that will determine our design. And maybe I should also mention that it would probably be helpful if we considered or thought about what is the exact design that we're looking at. And so let me just do a quick drawing. And in fact, let's get your quick drawing on this. So one of these things that I asked for is hardware, right? So just to see how you would do, let's take a break. And in this break, go ahead and get in groups of 4 and identify a simple hardware block diagram of this board you're designing. Not the whole system, just the board you're designing. We've gone over hardware block diagrams in this class, right? Was that yes or no? No. No, I haven't? Oh, okay. Well then, no, we won't break into groups. I'll just do it myself. All right, so hardware block diagram means that we're going to have a design, and what's going to be the center of our block diagram? All right, so we're going to have a microprocessor, microcontroller. So it'll be obviously an MSP 430, because we said we have to have our MSP 430. Now, what did we also say that this device would have? This was it, that's all I heard. Sensors, all right? How many?
5.
Ooh, 4, 5. What is it?
5.
All right, the requirement was it will be able to identify in all directions except up. So if you take a box, you're pointing 4 different directions towards the side and then up and down, and since we don't do up, it's 5. So we're obviously going to have sensors. And what else do we have?
Power supply.
A power supply. But what did I say about that in the power supply? I get it from the other board. So I have, coming from the other board, 5 volts, 3.3, and ground. What else do I have coming from that board over there? UART, all right? And UART implies RX and TX. And let's see, this will be, since it comes in here, that will be identified as RX for it, and this will be TX for this. All right? Oh, we don't have a battery over here. Don't we need a battery over here? Well, that's what these are, right? MSP 430. Do we need a crystal? Not really, because remember, it's built into this. Do we need, what else do we need? Do we need memory? Probably just use the memory that's on there, right? Which means we have to have enough memory on there. And then we had said 5 sensors. How are these sensors communicating with this? All right, exactly what is the signal? Digital or analog? Okay, you sure it's digital?
Yeah.
Okay. I don't understand what you're all saying digital, which is correct. And the people who took the qualifying exam, about 75% said analog. Are they overthinking this or what? You said digital because I said in the requirement digital pulse, right? So that obviously says digital. So that means that if we're going to connect between this and a sensor, how many wires do you need?
5.
How many? All right, let's take a look at what's the requirement here. What does it say happens with that digital signal? Requirement 2. Low mass ultrasound sensor that is digitally triggered. Microcontroller sends a pulse to activate, gets a pulse back when an object is detected. So it could be 2, could be 1. We'll go with 2. You could have 1 on the same wire. And in fact, that's how most of them work. But in this design, let's make it easy so it's not ugly. All right, we'll say 1. So let's put 1. And that's just a control wire. And gosh, why does that keep on doing that? I keep hitting the wrong button. I keep hitting video off rather than doc cam. All right, so here we are. What else do you think I need for this? Well, don't I need to power this? And I don't know what powers it, 3 volts or 5 volts, because I don't actually say that in the requirements, do I? All right, there we go. There's my hardware block diagram. But I do need to add some other things. So just for grins, I'll just call this P2.0, P2.1, P2.2, P2.3, P2.4. Can you see if anything else I need for this? I'll probably just call this D for digital signal, or actually P for pulse. That's it. It's done. Now, what did I not include in this design? The flight control board, right? Do I need to put like motor controllers and stuff like that on here? All right, why not? All right, the other board has it. Okay, why did the people who took this test not understand that? I mean, it seems really clear, and you obviously know this, but for some reason those that did the qualifying exam thought it very important to show the motors and the motor drivers and stuff like that. So, it's not that hard, is it? Okay? So now, you've seen MSP 430s before, and you know that they have different capabilities. So what do I know the capabilities that this chip needs to have? We definitely know we need a UART, right? And UARTs usually come as a transmit and receive. Do we need an ADD converter?
No. The sensor usually analog.
All right, now you're talking the sensor needs analog. I thought it said sensor needs digital. See, you're the one that you're one of those that took that qualifying exam, right? Do we need analog at all here? None. So I make sure that not needed. Analog, so we don't really need an ADC. If it's on there, that's okay, but we don't need it. Timer. How many?
One.
Just one? All right, how often are we sending information?
10 seconds.
All right, 10 per second. So obviously you need a timer that's going to run how much time?
100 milliseconds.
All right, so we definitely need a 0.1 second timer. Can you think of any other timer that you might need?
Well, you need a timer for the UART.
Do you need a timer for the UART? Well, that probably will work with the peripheral clock. So I'd say no, you don't need a timer for the UART. Unless you're creating your own UART, but we're getting a chip that has one. So it's a good thought. It's a good thinking. There's one other timer you need. What do you think that would be for?
To send data to forward of flight control.
Well, that's the UART, and that's handled by the peripheral clock. Give you a hint. Look at 3. All right, 3 and 5. All right, so An ultrasonic sensor is inherently based on what? Sound and time. So how do you know how long the signal has gone out and back? And hence why also here you notice that I provided you a little bit of extra information, and that was what? Speed of sound. So ultrasonic is, a chirp that goes out and comes back. Is that at such a high frequency you don't know what it is, or you can't hear it, but you know that it's going to run at 340 meters per second. Per second means time. It means you need a timer to record how long that is. All right? Now, a clever person would say, I would just let it chirp and then wait for it to come back. What happens if there's nothing in that direction? Will it ever come back? No. So what do you think you need to also have? Well, a timer that has a timeout aspect to it, right? So, do you really care if anything is further than 1 meter away? No. So obviously this means in our design that we're going to do our chirp, wait for the time that it would take for the chirp to go there and back, and if it doesn't come back by that time, just go on, so we know that way's safe. But if it comes back before then, actually, do we really care? If it comes back before then, how far away it is, if it's 0.9 meters or 0.5 meters, do we care the distance? According to the specs, we really don't care, do we? But it came back fast enough to say that there's something shorter than 1 meter there. And by the way, this is the speed this is sound, which means how long will that sound wavelength travel before we say we don't care? There and back. So 2 meters, right? So 2 meters at 3/4 meters per second, so it's a very short amount of time. So now we know in our system here, we're going to have another timer, and it's going to run for a certain amount of seconds that will help us identify when something didn't come back. Now, here's a question. How well do you know what ultrasound works? It works at a high frequency, right? Typically somewhere between 30 and 40 kilohertz. You can't hear it. Can you ping all 5 sensors at the same time? Okay, think about this. They're in different directions, that's right. What happens if you send all 5 at the same time? And then what happens? Well, what if it hits something, right? It'll come back and it will be measured by just one sensor, or might it be measured by several? It's possible it might be measured by several, depending on the shape of what it reflects off of. So with an ultrasound, you have to say ping, 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 ping. And do you have enough time to do that? It's part of the problem that you have to solve. So here we have now our hardware design, our capabilities. So let's look at the capabilities of a microcontroller. So what I'll do is I'll pull up a sheet of a microcontroller that says these are the different types of capabilities that your microcontroller will have. And this is a page out of the manual for a microprocessor. This is what we call a devices catalog. I don't think we need this. There we go. So here's the different things that allows you to choose. The part number, how much flash in kilobytes, how many bytes of SRAM. Isn't that funny? Bytes of SRAM. How many I/O pins are associated with this? How many timers? If it has a watchdog timer, a brownout, a I2C or SPI, a I2C SPI UART, a comparator. This is associated with A to D conversion. Have I talked about this, how you do that? With resistors, capacitors, draining it off. It's a pain, you don't want to know about it. If it has a temperature sensor, an ADC, A to D converter, right? Any additional features? Capacitive touch I/O. What else might it have? HF. What is HF? High frequency oscillator. Okay. And of course, price and the package it comes in. So what did we say we definitely need this thing to be able to do? UART, all right? So do any of these chips have a UART? All right, so obviously those are discounted immediately. And it's only the ones down at the bottom, all right? Does it care, do we care anything about this column, this column, this column, the A to D? Not really, so we don't care about that, all right? We do care about the number of timers it has, and we identified we needed 2, right? So, do these have 2? Oh yeah, they have 2. And how much memory do you think we need? And here's the question. Let's look at some of these aspects. This one has 2K and it's 60 cents. This one has 16K and it's 90 cents. Now, this is where a designer has to think, is it worth it for me to have lots of memory and pay 50% more for that part? Well, we don't know the application of this. Are we building one or millions? And this is where a designer has to look at what the goal of the design is. So if you're building one, do you really care about the price of volume? No, not really. So if we're talking about I'm building one, then I would say, I want to get all the memory I can get. I want to have all the timers I can get. Because I might need 3 timers. My algorithm might be such that I need 17K of code. Because I'm doing some fancy algorithms. And I'll pay the $1.30 versus the 60 cents. Big deal. However, if I'm building 1 million of these, that decision of mine just cost me how much? Double. How much? $700,000. That could have been profit that went into my pocket. So I choose something in the middle. So in this case, if I'm looking at, I probably need 3 timers. So if it were my choice, I would say, let me choose this one, which is the G2444, which has 8K of memory, 3 timers including 3 B timers, and it costs $1.05. And you could choose, but here's what I would say, and this is how I scored this, is that whatever you choose, you have to justify. And you have to have a reasonable definition of why you did this. I worked on a phone project where we woefully underestimated the amount of computing power we needed for the phone. And in the end, we had to overclock the processor and chew up lots of battery power doing that because we had a lot of computational intensive operations. And so you always have to make sure, the other thing is, at least we had a processor that allowed us to double clock it when you needed the processing power and then back off when you didn't. We paid a little bit more for that processor, but in the end we used its capabilities and it was worth it. So that's one aspect of, all right, what do we choose? And as I said here, just as they say in, let's see, Jones in The Last Crusade, choose wisely. All right, for the right reason. So now comes the next part of the assignment, and that was, now I'm going to have you start to work on this. Write the software interface description for communications between the embedded system and the board and the quad rotor. Now, what did we all agree that has to be done? You're sending a byte, right? And you're receiving probably a byte as well, right? Because I said UART. So now you have to identify what you're going to send one way or the other, how are you going to send it, and other concepts associated with the software interface. So that's what I want you to do for the next 5 minutes. Identify what you're going to send back and forth. All right? Get in groups of 4. We are back, and what I'm going to do is I'm going to cover a little bit of information. Here was the problem. Hey guys, they can't hear you, or they can hear you on the video. Software interface implies what? Well, we know it's UART, right? So it's questionable if the speed and bits and all that stuff is hardware or software, but be safe. Let's just identify it anyhow. So we know that we have a UART. So my software interface, I'm going to declare as the following. Well, first of all, I'm going to say I'm going to communicate at 19,200 bits per second. I'm going to, I could probably do 960 or 9,600. It doesn't matter. I'm going to have one stop bit, and I like parity, so I'm going to have odd parity. The other thing now I'm going to identify is send a byte. And I'm going to encode it as the following. Remember I said identify where there might be an obstacle or some sort of hazard. So so I'll say hazard forward. Hazard backward. Hazard port. Hazard, let's see, port and stern, right? No. Starboard, that's it. Hazard down. So this implies no hazard will be 000000000. So you're going to send a byte, encode, and this is once every 0.1 seconds. Response from the other side is going to be an ACK, will be 00001111, and a NAC is going to be 11110000. And there's our interface description. And I would address in the algorithm that if I got a knack, I would resend the byte again. In fact, I'll just say this, and resend. And that's how I would identify the software interface between the two boards. All right? Now, the rest of the problem, which I don't have time now, but it'll give you, we've already discussed it. Write the algorithms needed for the embedded system board to operate. This would be very good example to go ahead and do something like a what? What did we go over the last 2 days? A state machine. So being able to identify, oh, what mode are you on? You're in the waiting for the 0.1 second timer. Then you're in the gather the data. Then you're in the I transmitted the data to the flight controller board state. And then you're in the waiting for a response back and retransmit if needed state. And then you go back to the wait state. That would be a great way. This might be a very good example of something I might give on the final exam when I ask you to write the algorithms and the state machine and the, just the general concept. Yeah, this sounds really good. That's it. Enjoy the final.